Hi everyone, I'm ATEERA and today my friends and I will explain about transition metals. So let's meet our team first.
The objective of this video is to explain the concept of transition metals, describe electron configuration and general properties of transition metals, interpret the special characteristics of transition metals, and explain the basic metallurgy of iron.
So what is transition metals? Transition metals are elements found in the D block of the periodic table, specifically in the group 3 to 12. They are located between the S block and P block elements. What makes them special is that their atoms have partially filled D orbitals, or they can form ions with incomplete D subshells. One important characteristic of transition metals is the progressive filling of the 3D orbitals as we move across the period. Because of this, they show variable oxidation states, meaning they can form ions with different charges. Transition metals also known for forming colored compounds and ions, which is why many of the solutions appear blue, green, or even purple. In addition, they often exhibit magnetic properties due to unpaired d electrons. Due to these unique properties, transition metals are widely used in many fields such as construction, manufacturing, electronics, and medicine, making them very important in both industry and daily life. So, what about the first row of transition metals? The first row of transition metals is also known as the first transition series. It consists of elements from scandium to zinc, which are found in period 4 of the periodic table. The atomic number range from 21 to 30. Across the series, electrons are gradually added to the 3D subshell, which leads to strong trends in their chemical and physical properties. These include trends in oxidation states, magnetic behavior, and complex formation. Most elements in this series show multiple oxidation states, allowing them to participate in various chemical reactions. Many also form complex ions, especially with ligands such as water and ammonia. The first transition series show clear patterns that help chemists understand how transition metals behave in reactions and applications.
Next is electron configuration of atoms and ions. I will explain how to determine the electron configuration step by step. First, we look at the atomic number. For a neutral atom, the atomic number equals to the number of electrons. Based on the periodic table, atomic number of ion is 26, so ion has 26 electrons. Electrons are filled into subshell S, P, D, and F. Each subshell can hold S 2 electrons, P 6 electrons, D 10 electrons, and F 14 electrons. Based on periodic table, we can see group 1 to 2 have been filled in by S orbitals. Next is group 30 to 80 have been filled in by P orbitals. Next is transition metal, which is group 3 to 20 is D orbitals. Lastly is lanthanized and actinized, filling by F orbitals. Electrons are filled orbitals from lower energy to higher energy. Following the above principle, the common filling is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and the rest. For example, the electron configuration for neutral ion, which has 26 electrons, is 1s2, 2s2, 2p6, 3s2, 2p6, 4s2, 3d6, or in condensed notation, argon 3d6, 4s2. This arrangement shows electron filling orbital in energy levels with 6 electrons in the 3D subshell and 2 in the outer 4s subshell, explaining its property as a transition metal.
But they have some special case in this electron configuration. For example, some elements do not follow the normal order. For chromium, instead of argon 3d4 4s2, the actual configuration is 3d5 4s1. This is because a half-filled D subshell is more stable. Another is copper. Instead of argon 3d9 4s2, the configuration is 3d10 4s1. A fully filled D subshell gives extra stability.
Next, I will explain the general properties and trend in transition metal. First, atomic size. In transition metals, atomic size across the period decreases slightly at first and then becomes almost constant due to increasing nuclear charge while electrons are added into any 3D subshell, which provides pole shielding. For example, iron in period 4 has an atomic size that is only slightly smaller than manganese and similar to cobalt. This shows that the atomic size does not decrease significantly across the transition series because the increasing nuclear charge is partially offset by pole shielding from 3D electrons. Going down the group, atomic size increases from period 4 to period 5 due to the addition of a new electron shell. However, from period 5 to period 6, atomic size remains almost constant due to lanthanide contraction. Lanthanide contraction occurs because 4f electrons shoot very poorly, leading to an increased effective nuclear charge, which pulls the outer electrons closer to the nucleus and result in a smaller than expected atomic size. For example, iron is noticeably smaller than ruthenium, but has a smaller atomic size to osmium, despite osmium being in a lower period. Next, ionization energy. The ionization energy of transition metals increases slightly across a period. This is due to the increase in nuclear charge and the gradual decrease in atomic size, which cause valence electrons to be more strongly attracted to the nucleus and therefore harder to remove. For example, the ionization energy of iron is slightly higher than manganese but comparable to cobalt. This reflects the gradual increase in effective nuclear charge across the period, which makes the valence electrons more difficult to remove. Going down the group, ionization energy generally increases slightly, which is unusual compared to main group elements. This trend is caused by two main factors. First, there is only a small increase in atomic size because added electrons enter inner d orbitals rather than significantly expanding the outer shell. Second, there is a large increase in nuclear charge as the number of protons increases down the group. Since the electrons do not effectively shield the nuclear charge, the attraction between the nucleus and the outer electrons becomes stronger. As a result, more energy is required to remove an electron, leading to a slight increase in ionization energy. For example, iron has a lower ionization energy than ruthenium and osmium, even though these elements are located in lower periods. The third one, electronegativity. The electronegativity of transition metal increases slightly across a period due to the increasing nuclear charge, which enhances the attraction for bonding electrons. For example, iron is more electronegative than manganese, but slightly less electronegative than cobalt, which follows the increasing trend across period 4 transition metals. Going down the group, electronegativity increases from period 4 to period 5 but remains almost constant from period 5 to period 6. Thus, iron has a lower electronegativity compared to ruthenium, while ruthenium and osmium show very similar electronegativity values due to lengthened contraction.
Iron commonly has two oxidation states, +2 and +3. The +2 state, called ferrous, is found in compounds like iron sulfate, while the +3 state, called ferric, is seen in rust and ions such as hexacyanoferric 3. Iron can also exist in the less common +6 oxidation states found in the ferrite 6 ion. Iron shows different oxidation states because it is a transition metal. It is 4s and 3d electrons have similar energies, allowing iron to lose different numbers of electrons. Iron is known to be a transition element, and the reason for the formation of colored compounds is that the ions of iron, namely iron 2+ and iron 3+, contain partially filled d orbitals. The d orbitals of ions help in the absorption of certain range of visible light, and due to this phenomenon, green color in iron 2+. This occurs because of d orbital splitting. When ligands such as water molecules bind with the iron, the d orbitals experience splitting of different energy levels. The electrons in the lower energy d orbitals can absorb energy from visible light and occupy the higher energy d orbitals. The color observed is called the complementary color of the light absorbed, since iron can also have different oxidation numbers, like iron 2+ or iron 3+. It resulted in a variation in difference in level of energies between its d orbitals, because of which different lights are absorbed along with different energies. Ion in formation of complex ions. Transition metals readily form complex ions because they have empty orbitals and high charge density. Ligands donate lone pairs of electrons to the metal ion to form coordinate bonds, while other metals can form complexes. Transition metals form a much wider variety due to their partially filled d orbitals. Transition metals such as iron are very good catalysts. This is due to because they have partially filled d orbitals. They have multiple oxidation states. These two characteristics enable them to form temporary bonds, as well as provide active sites to the reactants to result in the reductions of activation energy. For instance, in the Haber process, iron in its solid state behave as a heterogeneous catalyst to enable nitrogen and hydrogen gases to combine to form ammonia gas. Iron can be useful in homogeneous catalysts. This is because iron 2 ions can act as catalysts for reactions that involve the oxidation state changes of persulfate ions and iodide ions. Iron and other transition metals catalyzes chemical reactions through changes in their electron configurations and acting as surfaces for the reactions, thereby increasing the efficiency of industrial reactions.
So now, we are looking at the metallurgy of iron. One of the most important things to understand about iron is that it is rarely found in its pure, metallic form in nature. Because iron is reactive, it dwells or exists combined with other elements, as you can see in the green box. Down there, iron ores are naturally found as oxides, carbonate or sulfides, and they always contain impurities like rock or soil that must be removed. To get the iron we use in everything from skyscraper to cars, we have to start with the main ores. There are 4 primary minerals displayed here. The first one is hematite. This one is the most important iron oxide, and it is often reddish brown and is a primary source for the world's iron production. Second one is magnetite. As the name suggests, this ore is naturally magnetic. It has a very high iron content and is typically black or dark grey. The third one is diorite. Unlike the oxide, this is a carbonate ore. It is a valuable source of iron, so it generally contains less iron by weight than hematite or magnetite. The last one is iron pyrites, commonly known as fool's gold because of its metallic luster and a pale brisk yellow hue. While it contains iron, it is actually used more often Its sulfur contained then for making iron metals. Now that we know what the primary iron ore are, let's look at the three major steps required to extract pure iron from the earth. This process uses intense heat and chemical reaction to turn rocky ore into gleaming metal. The step 1 is concentration. It is the first stage where we prepare the raw material. Crushing, the bulky ore is first fed into crushers and broken down into small manageable pieces. Gravity separation. These pieces are then washed with water. Because iron ore is much denser than the gangue, the unwanted clay and the sand, the impurities are washed away while the heavy iron-rich particles remain. Next is calcination. The concentrated ore is heated strongly but specifically in the absence of air. This process helps remove moisture and volatile impurities like sulfur or arsenic, and it decomposes carbonate like siderite into oxide, making the ore porous and ready for the final stage. Step 3 is melting, the final and the most critical stage, the mixture. The silcine ore is mixed with a calculated amount of coke which acts as the fill and reducing agent, and limestone which help remove remaining impurities as slag. The blast furnace. This mixture is fed into the top of blast furnace. Under intense heat, the carbon in the coke breathes life into the ore by stripping away the oxygen, finally leaving us with liquid iron. Now, let's look inside the furnace to see how the chemistry works. These are two main chemical phases occurring simultaneously. Phase A is the formation of carbon monoxide. Before the ore can be reduced, we must create a reducing agent. Coke burns in the air at roughly 1875 K, producing heat and carbon dioxide. C plus O2 right arrow, CO2 plus heat. The CO2 then reacts with more coke to be reduced with carbon monoxide. C plus CO2 right arrow to CO. Phase B, reduction of ores to iron. Once we have carbon monoxide, the actual extraction of iron begins. The carbon monoxide CO reduces the iron ore. For hematite, the reaction is Fe2O3 plus 3CO right arrow to Fe plus 3CO2. For magnetite, the reaction is Fe3O4 plus 4CO right arrow 3Fe plus 4CO2. The resulting molten iron sinks and is collected at the very bottom of the furnace, while the impurities form slags, which is collected separately. You might be wondering why we add limestone to the mix, right? It's actually act as a flux to help remove the remaining sand from the ore. Inside the furnace, limestone CaCO3 decomposes due to heat into calcium oxide CaO plus CO2, CaCO3 plus heat right arrow CaO plus CO2. This calcium oxide then reacts with the silica sand present in the ore to form the liquid slag. CaO plus SiO2 right arrow SCA SiO3. Because the slag is liquid and lighter than iron, it floats on top of the molten metals, allowing us to drain it off separately. Now that we have successfully extracted iron from its ore in the blast furnace, we need to understand the different forms it takes. The primary difference between these forms is their carbon content, which drastically change how the metal behaves. First, we have cast iron. This is the immediate product of the smelting process. It contains 2 to 5% of carbon, along with the trace of other impurities. Because of this high carbon content, it is very hard but also brittle, making it ideal for casting into specific shapes like pipes or engine blocks. Next is wrought iron, which is considered as the purest form of iron. It contains a very small amount of carbon, only about 0.25%. Being nearly pure, iron makes it much tougher and more malleable than cast iron, which is why it was historically used for decorative gates and structural rivet. Finally, we have steel, which is perhaps the most versatile and widely used form of iron today. Steel contains between 0.5 to 1.5% carbon, along with varying amounts of other elements like manganese or chromium to give it specific properties. By carefully controlling this carbon percentage, we can create a metal that is both incredibly strong and flexible enough for skyscraper and bridges.
In conclusion, transition metals are diploid elements with unique physical and chemical properties. Their partially filled d orbital allow them to show variable oxidation states, form color compounds, and produce complex ions. These features make transition metals important as catalysts in many biological and industrial applications, highlighting the significance of their electronic structure in determining chemical behavior.